So the next speaker is Dr. Gabriel Figueiras. He's from Physics Department of Porto University, and he collaborates with the University of Aveiro, and he's going to present his talk on radio frequency sputtered ferroelectric oxides. Well, please, I invite Fábio, Dr. Fábio on stage.
Okay, good afternoon again. Here I'm presenting a new material called double perovskites made of bismuth, zinc, and titanate. And as an oxide, it is a really interesting material. And it was the point is that this material as an oxide has a narrow band gap. Usually perovskites will have like bismuth ferrite, and others will have a very high band gap. And why is this interesting? Because as you will see now, the interest of making photovoltaics with new materials, there are lots of materials to be used in photovoltaics, and most of them have advances, of course, and some problems. And I'm talking about that most materials that are used for photovoltaics, like silicon, are well tested and are commercially available, but have problems with the limitations of how much energy can be produced from the sun. Well, the solution has to be joining many semiconductors to produce a multi-junction. Each junction will be not very effective, but altogether they will catch more from the sun. Of course, if you join more cells together, it means it's more costly, but they will work on the same manner. So there are alternatives and other semiconductors, and the semiconductors that are using selenium, cadmium, tellurium are really well performant, but have problems with environmental issues, rare materials, expensive materials. So and they also work in the same way as semiconductors with a p-n junction. So the most promising materials are now for photovoltaics are organics and they're hybrids. And the cost is very low. They appear to be the solution, but in fact, they are facing lots of problems with stability and homogeneity. And most of them will not stand as organics. They will not stand for high temperatures or even UV light. So my point is like out of the box of the traditional these materials. Organic inorganics are not traditional, but they have limitations. So where do I go now? My proposal is to find an oxide with a narrow band gap that will replace silicon or works. But most oxides, especially ferroelectric oxides, will have a very high band gap. So join other things that I need that material to use a ferroelectricity instead of a p-n junction. So if a p-n junction, what it does an electric field that separates electrons from holes from the photogenerator. So if I put the electric field from polarization, I can avoid the p-n junction. So I don't have to pay the expenses of energy and limitations of how much voltage I can take from a cell, or how low voltage. They it can never be lower than the p-n junction barrier. So and in the end of all, I go for oxides that are from really available materials, and if they are oxides, they will not be unstable like the organics. And let's use materials that are not so dangerous like platinum. So here I go. I present these new materials with added added possibilities. They are ferroelectrics. They have a low band gap, and as they are ferroelectrics, they can use another properties like piezoelectricity or thermoelectric for harvesting energy. And if they are oxides, they will be accessible. And as oxides, we all know that they are easy to produce. So this study, how I discovered these materials. So after studying a lot of materials with DFT simulations, there are a few that seems very interesting. Bismuth-based double perovskite oxides. So what we have a non-central symmetric structure that promotes ferroelectricity, and the difference between two ions on B side will have the difference in chemical element, and as ionic, they will generate two sublattices which will have different conduction and lower the band gap. So in the present, very good results with bismuth, ferrium, chromium oxides have reached already photovoltaics pre-prototypes reaching 80.1% of efficiency. So I go for another material, bismuth, zinc, titanium oxides. This material makes highly asymmetric bonds between zinc and titanium. The charge will be, the arrangement of charge will be very displaced, meaning that it promotes ferroelectricity and very high polarization. And the band gaps allows below 1.5 electron volts. So these other materials are also possible, but zinc and titanium are more accessible than vanadium, for instance, and much easier to handle in production. What's the catch? The bismuth perovskites are not easily stabilized on room pressure, room temperature. So sintering these materials, putting bismuth oxide, zinc and titanium together will probably get you another material that is not a perovskite alone, a single phase. So we go for RF sputtering, inducing the phase in a film, and the high strain of the film should stabilize this material. And so there was a very long practical and experimental research for a theoretical material. And our results demonstrate that we try to produce the material at very high temperature or from very low temperature. And what we got is that the material at low temperature is almost amorphous. The material at medium temperature will start to form the film in an epitaxial way, but it still has much amorphous and double other phases. And so let's try to anneal this material, and it turns out to be another oxide, bismuth 4 phase. And we have a very narrow window between 500 degrees C and 550 that can really make this phase to stabilize. And so you can imagine that we made lots of samples and lots of substrates until we found the right conditions to check this material. So I will now focus on do we really have this material that is not so easy to stabilize as a bulk form, only in high pressure? So we made lots of studies in terms of electron microscopy, checking the material composition, and in terms of second harmonic generator, to understand if the real material was really ferroelectric or at least non-central symmetric. High success in these measurements prove that the material has a tetragonal phase, a really difference between C and A parameters, promising a high ferroelectricity. So let's check this, and we found that the material has a band gap exactly in the range that was predicted by the studies and DFT studies, and the other materials with different phases, either the amorphous or the secondary phase, completely fail the band gap. So this is also encouraging. We got the right crystalline structure, we got the right band gap. So we go now for piezo force microscopy. We got imprints, and especially we have the hysteresis loops that are demonstrative that the material has ferroelectric properties. So while when you compare to other films that are made from the same target, the same material, they will fail to have the properties that are predicted. So this research was published in the Journal of Material Chemistry and last year. And I advise you to, if you are working in photovoltaics and perovskites, this is something to look for, because it's an alternative to the organics or hybrids. So as to finish my presentation, my highlight is that you are able to produce a new material, let's say, that material that was predicted by DFT is not easy to fabricate ceramics, so we produce it by RF sputtering into silicon-based substrates. Our many experience in characterizing these films show that this phase that we got is the predicted bismuth to zinc oxide double perovskite. And now we go for the second part of our work, searching for an application and trying to do a prototype on this material. So thank you very much for your attention. I hope you have questions, please. Hello?
Well, thank you.
I hope it was fast. Everybody wants to go to lunch.
Yeah, it was very quick, actually.
Yeah.
But does anyone have questions? Wow. No questions again. Well, it seems that your presentation was clear enough for people to understand everything.
Yeah, it is a very straight experimental work, lots of lab, and the real work, well, I think it will start now trying to do something about it, something more practical.
But can I ask you one thing? In photovoltaics, you would have a stacking of different components to broaden the absorption of light.
Yes.
And in which position this particular system shows up in this perspective?
So this is the absorber. This is the material that is absorbing, and it has the properties for the photon generation of electron and holes. And the holes will go by the titanium percolation, and the electrons will go by the zinc percolation. So these materials can split, and then the material has a ferroelectric properties. It can have a polarization. If we fix the polarization between the electrodes, the electrons will and the holes will be split inside the material itself. It does not need a p-n junction. It's a single material, and all it should need is the electrodes on top and bottom, and it makes the absorption, it makes the driving, and it makes the splitting. It's all in one. So it has the properties to do this. Now, if it works, of course, we have to do a prototype, and this requires much more money, or let's say more investment, to do a prototype than to prove that we can do a material in a practical way. Did you understand?
So you don't need to combine it with the other materials. So it's just standalone, this material with electrodes and in principle,
we need to combine with the electrodes, yes,
electrodes.
Of course, and the transparent substrate, transparent electrodes. But it should be operative on its own. Of course, it can take interlayers between the electrodes and this material to help minimizing Schottky barriers and other defects that will happen in the interfaces. And of course, that's how I was saying, doing a prototype is not so simple as doing the material alone. And having this material alone is already a progress, but the prototype will need another deep studies.
Okay, okay. Thank you.
Thank you.